Hello, welcome to Numerical Ship and Offshore Hydrodynamic course. Today is a lecture 32 and we are going to discuss just continue from our last discussion, how do I develop numerically to write this simple response function code. Okay. So, these are the keyword that you have to press to get this lecture. Okay. So, now let us discuss that how we can develop this code. Now, here if you remember in my last class, what we did is, let me write this equation again. It is m plus a. Now, I understand it is infinity. Now, I write infinity for this x double dot plus 0 to infinity, then b tau x dot t minus tau into d tau plus C x equal to external function. So, this is how we can get. Now, here also you understand that from this equation I get b tau equal to 2 by pi 0 to infinity, then b omega cos of omega tau into d omega. So, let me write this equation number 1, let us say this equation number 2, and also this a infinity I can get from the equation, we can call this a omega and then plus 1 upon omega into 0 to infinity into b tau into sin omega tau into d tau. So, you can call this equation 3. So, to solve equation 1, a priori we need to understand how I get this b tau and how I get this a infinity. So, we did not talk about how I get this a infinity, today we are going to discuss, but here in the last class what we discussed as follows, that this b 0 that I can get simply trapezoidal or Simpson rule, and it is nothing but 0 to some omega n, right, into it is b omega into d omega. So, that is how we can going to get this b 0, and then we have lot of discussions on how we can set that tau n, because we understand that for the large tau this whole expression goes to 0. So, therefore, even if this integration limit is infinity here, I can understand here also in this equation that integration limit is infinity, but however, it should be some finite value tau n, and you can call this could be is equal to some multiple integer multiplied by the delta tau. So, that we understood. Similarly, also we understand that from this graph of b omega, this graph also cannot be infinitely long, because at higher omega. So, at some omega n this curve also approaches to 0. So, therefore, even if this limit cannot be infinity, it should be some finite limit omega n, and similarly I can call this maybe this omega n definitely some integer n multiplied by the delta omega, kind of this. Now, we need to, because see at the end we need to convert this into some kind of numerical technique. So, therefore, we have to add certain things, right. So, we have to use this summation term. So, while doing this summation term, that time I know that at which n I should apply this summation form, or at which m I should apply this summation. Okay. So, that we discussed the last class. So, today let us try to find out numerically how could I get this solution for b tau. So, just write it again. So, now I do not write it to infinity. So, I write some 0 to omega n here b omega into cos of omega tau into d omega, I just write it. And then what we discussed in the last class, that here how I approach this b omega, the small b omega curve. So, now there are several way of approximation, right. So, this is omega and let us say this is omega n, and if this is the curve of my b omega. Now, what we discussed last class, we split into several sections here, and within this section we assume this b omega graph is linear. This b omega graph is linear. Now, once we approximate this b omega curve should be linear. So, now let us define something, let us take some arbitrary interval. So, let us take some arbitrary interval, this omega I minus so 1 comma omega I. Let us take this arbitrary interval. Okay. Now, in this arbitrary interval, then how I write a equation for a straight line. So, as I said that initially we thought of having it a constant to prove that this b tau goes to 0 when tau goes to infinity. But now here in reality, see here we can apply many things, we can apply quadratic curve also, right. But that time you need if you want to do the cubic spline, then you need to have 2 points and also the 2 slope at 2 end points, right. And in quadratic also you need at least 3 intervals. So, some intermediate point is required. So, many things we can do. We do the simplest way, we assume it should be a straight line between 2 intervals. Okay. So, then how I write it is, everybody knows it is a straight line equation. See b omega minus b of omega I minus 1, right. Okay. Before that, for convenience, let us define my d omega I is equal to omega I minus omega I minus 1, and also let us define delta b equal to b of omega I minus b of omega I minus 1. So, let us define this. So, then it should be equal to delta b by delta omega. Okay, you can call this I, here also I just write here I into omega minus omega I minus 1, is it not? So, therefore, I can assume my solution of b omega, it should be a b of omega I minus 1 plus, now I can call this as m I into omega minus omega I minus 1, or to be very specific. So, now I can call this b omega equal to, now this and this term is constants. Okay. So, I just again split into 2 terms. So, I can call m I into omega, then plus b into omega I minus 1 minus m I into omega I minus 1. I do this, and this actually we can call some constant. So, I can call it C I. So, finally, I have b omega equal to m I into omega plus C into I. So, that is how actually I can write the equation in the interval between omega I minus 1 to omega I, right. So, having said that, now what I do is this b tau I split into several intervals. So, I started with 0 to omega 1, and each interval I am performing this operation integration b omega cos of omega tau into d omega. Okay. Of course, 2 by pi is in the front, right. So, then I just fit it this way. So, then it is omega 1 to omega 2 into b of omega into. Okay. So, I just make one thing, I just make this whole thing 2 by pi outside. So, it is cos of omega tau into d omega and so on. So, in the ith interval it should be omega I minus 1 to omega I, right, and then it is again b omega into cos of omega tau into d omega plus till the nth term. So, then things actually I can write in more simple way, it should be then 2 by pi into summation I can take I equal to 1 to capital N. That is what I talked about, like when this, that is why I write that your omega n should be n into some delta omega, right. So, then is 2 by pi and you can call it is I. So, this is how actually I can express this b tau very nicely, right. And then the expression for I it is nothing but this integral into omega I minus 1 to omega I into b omega cos of omega tau into d omega. So, this is how actually I can think of doing it. Okay. So, now find out this integral I which is nothing but it is omega I minus 1 to omega I into b omega into cos of omega tau into d omega. Now, you see that this is now I think it is elementary. Why? Because now I just write the expression, I assume this is the linear interpolation. I will tell you that final expressions, mathematical expressions are easy, right, but this final expression requires some kind of approximation technique, some kind of simplifications, right. So, it is up to the who is writing the code, right. Now, if you take is a quadratic function this b omega between two interval, then you can take a bigger patch, so that you afford to take care about the curvature of the b omega. Now, then the solution become little bit more complex, the expression comes little bit more complex. Now, if you consider the it is a linear, then you can't afford to take a longer delta omega because of this the curvature of the curve. So, here if you take assume is as a straight line, then definitely this interval become very small. So, you can say that within this short interval this variation of this b omega can be considered as linear. So, this depend on the coder, like who is writing the code, their understanding, their expertise, the experience, everything actually comes to that is why it is a very small thing, like but then how you can define this this small interval omega I minus 1 to omega I, that is also not that easy, I would say, because you need to check lot of things, that whether this solution is convergent enough or not with respect to that interval, right. So many things are there. But anyway, once you find out that interval and all, the remaining part is trivial, right. So, now here what we need to do is this omega minus 1 to omega I. So, I just check that what this is the expression for my b omega. So, let me use this expression. So, here it is some m I into omega plus C I, and then it is cos of omega tau into d omega. Now, you see the things are very trivial. So, we have two interval, one is omega I minus 1 to omega I. So, I just take out the C I outside, it should be cos of omega tau into d omega, and second one is plus, I can take out this m I outside the integration sign. So, it is omega I minus 1 to omega I. Now, you have omega into cos of omega tau into d omega. So, this is the thing that you have. Now, this is integration is trivial, it is sin omega tau, and here so you have to do little bit more mathematical work to this integration by parts you need to do to find out, right. I know that this you know very well these things, but still for the completeness. So, the first case this equal to then sine of so C I is there. So, then it is sine of omega tau by tau. So, I just write tau over here, and then it is omega I minus 1 to omega I, and then it is plus, then I have m I, and then this. So, you take this as a first function, second function, so and then you can carry on. So, it should be omega into sin omega tau by tau, and then this limit is omega I minus 1 to omega I, and then minus, then is the integration again, it is omega I minus 1 to omega I. So, it is 1 upon tau into sin omega tau into d omega, right. So, now here, so I just let me leave it like this way. It is only these expressions become bigger because computer is doing it. So, anyways, so it is m I by tau, and then it is omega sin of omega tau, and then it is plus, it is now here we have uh, 1 upon tau already. So, it is m I by tau square, it is cos of omega tau into omega I minus 1 to omega I. Now, why I am actually these things I am not interested, like this is okay, fine, its computer will do that. That the important part is the nature actually I am able to capture. Now, here you can see this, it is divided by tau and this is divided by tau square. So, this confirms me that when tau goes to infinity, because this under the square bracket, this term are constant, I mean lying between minus 1 to plus 1 or something, for a higher omega maybe little bit more. However, denominator is rapidly go to infinity, right. So, therefore, the overall contribution become 0 at tau goes to infinity. So, this nature is very much visible here also. So, finally, once I know this term I, so then I just perform the integration, I can get it is 2 by pi into sum of I equal to 1 to n to I. So, now this is how I get the solution for beta. Now, definitely in fact, maybe in future classes, maybe next or next to next class, I am going to show all kind of nature of this curve b tau and then a infinity, how to calculate this. Okay. Then it will actually you can see that how this curve varies, because later on when you develop this code, then actually you can see for a comparison, okay, this would be the nature of the curve, whether it is following it or not. Okay. Anyway, so now I know how to get the b tau, but secondly you need to find out how to get the a infinity. Now, it is a infinite frequency domain, infinite frequency added mass. So, it is actually a geometric property, right. Now, if you remember our first the introduction to this numerical method started with a infinite domain problem, where when we take a object floating in inside a ocean, right, this I mean this is inside a ocean, and then we try to find out the added mass of this object, right, that we did, right. Actually, this is the same problem actually you can use, like if you have this z equal to 0, and then if you take this object and then its image, and then you are solving the same problem for infinite frequency, that infinite depth problem that we did, right. We take that g equal to 1 upon r and we have solved that problem, right. You remember it, right, initially. So, I think that I mean that is the key. I mean if you have that code with you, so then this is your infinite added mass. Only thing, the geometry you need to put over here, and then it is the weighted surface, and you take the image part and then you solve this with this Green's function, and then simply solve this boundary value problem, then you get this infinite frequency added mass. Okay. Since we have already discussed that there, really we do not discuss over here, but there are some popular software available here like Orcaflex. I think they show that infinitely frequency added mass through this Cummins equation again. Now, if you remember in the last class I leave this way, it is minus a omega, I can do this, it is minus a plus omega into 0 to infinity, and it is we have b tau into sine of omega tau into d tau, right. And then I can write this a equal to, okay, it is not omega, it is 1 upon omega. So, a equal to a omega plus 1 upon omega 0 to infinity b tau into sine omega tau t tau. Now, before we try to find out the a, we must have the value for b tau, which I just discussed how to get the value for b tau. Okay. And then we need to find out this added mass for each frequency. Now, what is happening, what I am going to do is as follows. I am trying to plot this function a with respect to all omega. Okay. So, that is actually my objective, right. So, how to proceed? Now, here let me write again this a equal to a omega plus 1 upon omega into 0 to infinity multiply by b tau into sine of omega tau into d tau. So, this is my equation, right. Now, what I said, I need to apply for, I try to find out A for each this omega. Now, I have this solution for A omega, I have this solution for A omega for each I. So, that means what I have with me for each omega I have this solution for omega I. So, this list I have. So, therefore, for some particular, let us say omega I, my added mass is the frequency of an added mass is A omega I. Now, remember this equation is satisfied for all omega, right. So, what I did is, so first then actually for each omega I can solve this A omega I plus 1 upon omega I, then 0 to infinity into b tau, then sine of omega I into tau into d tau. I perform this. For each omega I perform this equation, let us say 2 numerically to get the solution for A, and then I see the how the graph looks like. Now, mostly why I am looking it, I try to find out when at which omega this value of A become constant, like. So, I expect this graph will some kind of this. Now, when here it is, let us say some omega k, if this is the value for A and it is, let us say omega k plus delta k, if this is the value of k. Now, if the value of A at omega k minus A omega k minus 1, if this value is less than epsilon, okay, if this is the value less than epsilon. So, I that point of time I can say this is my infinite frequency added mass A infinity, right. So, the idea is I am applying this omega k, I mean for a particular omega I am doing this integration, and definitely it is not infinity now, I understand it should be some tau m, some finite tau m and b tau into sine of omega k tau into d tau. Now, how to perform this? So, it is very simple, I do that, I perform each omega k and I see the graph. When I can see this graph is is a constant. So, that time I call. So, this is it is my A infinity, because A at omega k minus A at omega k minus 1, if you take a mod, this less than sum of epsilon, which is my choice, fine. Now, this whole thing, the whole exercise remain how I can model this integration. So, now I also know how to do this, because just right now the similar way I did that for b tau, right. Here the thing is that I define my this integration again I can write as A into omega k plus 1 by omega k, and then it is summation I equal to 1 to some m, right, because I said that my tau m equal to m into some delta tau, right. So, then it is integration of some I where I is nothing but at interval it is tau I minus 1 to tau and then b tau into sine omega k into tau into d tau. We know that now how to do this, right, because again I assume this b tau is a straight line. So, I can say b tau minus b tau I minus 1 equal to some m dash, right, I with some m dash I into omega sorry, now in this case tau minus tau I minus 1. So, I write this equation, I substitute this equation here and again I know that how to do this analytically, right. So, now today's class what we understand that how to get the solution for b tau and then solution for a infinity using I am not doing this for infinite frequency panel method, that you can do from that also, but this is other way of doing it. You plot the graph, get that where it is convergence, and that is your A infinity, right. So, and then so now today I know that how to get these two parameter, but still I need to solve this the whole equation of motion, right, and that involves the convolution integration also. So, in the next class we are going to discuss that. Thank you.